We hope you can get really comfortable using the eigenvalue techniques to solve systems of equations. It's a nice technique, and one that you probably want to know because we might test you on it. Actually, we will. All right, so what are the things that can happen? Well, you can have distinct real eigenvalues. Okay, great. Find the eigenvectors. You can have complex eigenvalues. Oh, that's interesting. And then you can have repeated eigenvalues, which is also interesting. So we want to talk about these two and do a little bit more practice. And of course, the more practice we get, the more comfortable we'll get, and the more confident we'll be that we can do really well. All right, well, let's get going. So let's start with the following problem. Find the solutions x of t and y of t of the system of differential equations. X prime equals x minus 2y, y prime equals 2x plus y, with initial conditions x of 0 equals 1 and y of 0 equals negative 1. Now I'm going to just make a note here. When we see a problem, we don't know what type of eigenvalues we're going to encounter. It's really hard to see beforehand. And so you just have to go through and work the process. So again, here's 3 different scenarios. Each one is slightly different. Let's find out which one we're in. So we're going to switch this into a more matrix-friendly way to write this. And in that way, we're going to write this as x prime, which stands for the derivatives. Now, you can't really tell by the way I'm writing this, but this is actually a bold x. See how bold that x is looking? Yeah, that's a very bold x. And then we grab our coefficients, and then we have x. All right, so that's our system as a matrix. So now let's start doing the eigenvalues. All right, so we're going to take our determinant, a minus lambda I, and we get that this is 1 minus lambda times 1 minus lambda. That's 1 minus lambda squared. And subtract 2 times minus 2. I actually make this plus 4. And now we're like, wow, they gave us a gift. You might say, well, what gift did they give us? Notice this is lambda minus 1 squared plus 2 squared. The gift is they already put it as a perfect square, complete the square. And so from here, we actually can just say, oh, these are really simple eigenvalues, right? Because that says, aha, lambda minus 1 quantity squared equals minus 2 squared. So lambda minus 1 is plus or minus 2y, because we're taking the square root of both sides. The minus is where the I comes from. So our eigenvalues are 1 plus minus 2i. All right, so now we know we are in the eigenvalue setting. Okay, well, that's good to know. It's good to know what type of problem we're doing. Say, all right, great, what's next? Well, next up are eigenvectors. Okay, so for that, what do? Well, we're going to take our a minus lambda I, where this is our lambda. Well, in particular, we're going to do 1 plus 2i. And say, okay, so we take 1 minus 1 plus 2i, and minus 2, and 2, and 1 minus 1 plus 2i. And if we do that, which we are, that's what we're doing right now, we see, hey, this simplifies. This becomes a minus 2i, and a minus 2, and a 2, and a minus 2i. All right, now to find our eigenvectors, well, remember, we just need to find one of them. We say, hey, now you take this, and you ask yourself a question. What can I multiply by and get out 0, 0? So we look at this and say, okay, well, one way is to say, all right, take this row and just sort of write it, if it's this way, we're going to write it going in the opposite way. So minus 2i, 2, and then flip the sign. So I'll flip the sign here. So it becomes a plus 2i. And we're done. That's our eigenvector. You can check, right? It'll become minus 4i plus 4i is 0. Life is good. All right, so our eigenvector, 2i, but we can, of course, scale. So let's divide by 2, 1i. And now say, hey, wait a second. We need to break that apart. So we say this is the real part. So you say, okay, what's, think of this as a plus bi. So in fact, we'll make it really explicit. It's 1 plus 0i and 0 plus 1i. So when we talk about the real part, that's the 1, 0. Talk about the imaginary part, that's what's attached to the I, that's 0, 1. So this becomes 1, 0 plus I, 0, 1. And good. All right, now, the next thing we need to do is to work on our general form. All right, so we'll sort of block this off. Now, our general form, we need our pieces. And the way we do our pieces is we take our eigenvalue. So here's our eigenvalue. And we combine that with information about our eigenvector. So here's our eigenvector. And we say what? Well, what we'll do is we'll use e to the eigenvalue t, which becomes e to the t cosine 2t plus I e to the t sine of 2t. All right, so that's e to the eigenvalue t times the eigenvector that's been broken up. So times 1, 0 plus I, 0, 1. Okay, so that leads us to saying x equals, and now we multiply out. There's really 4 terms, right? Because there's the first, there's the outer, there's the inner, there's the last, FOIL. And we group by whether the result is a real or complex. So the real parts will come together, and I'll put an a in front. And so we have e to the t cosine 2t times 1, 0. Okay, so we'll write that down. And the other part that will make it a real part is the imaginary pieces. So the I times I becomes I squared, which means a minus e to the t sine 2t, 0, 1. Okay, so that's the first part. Now the second part, grab the imaginary pieces. So the first with the last, or if you like, the outer pieces. So that's e to the t cosine 2t, 0, 1, and the inner pieces, which is the e to the t sine of 2t, 1, 0. Good. Now, somebody wants to ask, hey, where does the I go, right? Because when you multiply, you get the i's. Well, the i's got absorbed into the b is one way to think of it. All right. Now, if we were asked for the general solution, we'd be done. But we weren't. We were asked for the particular solution, and we were also asked x and y not as a system. So, well, we should clean this up. So let's rewrite this as a system. So first off, what does our x function look like? So that's, see, this x here, this is where it gets confusing because we use x as a vector and then x as a function. It's so much clearer when it's written because there's a bold x or the vector, but take my word for it. I'm not lying to you. All right, so we grab the tops. So we have a e to the t cosine 2t, and then 0, then 0, and then a plus a b e to the t sine 2t. Great. And y, well, that's the bottom. So we get 0, then we have a minus a e to the t sine 2t. So I'm just putting underneath the other e to the t sine 2t. See the minus a. And then a plus b e to the t cosine 2t. And now we plug in our initial conditions. And we say, well, x of 0 is supposed to be 1. But when we plug it in here, the sign goes away. That all becomes 1. So we get a equals 1. And y of 0, well, that's supposed to be negative 1. Okay, well, that becomes b. And the other part goes away. So now we have a and b. And therefore, we can say our final answer, x equals e to the t cosine of 2t plus e to the t sine of 2t. And y equals, well, minus e to the t cosine of 2t and minus e to the t sine of 2t. So it turns out that x was the opposite sign of y, or vice versa. Who knew? It's not so clear a priori, but that's all right. We don't need to know beforehand. It just comes out. The process works. Process works. So recapping, what do we do when there's a complex eigenvalue? Well, we make sure we find the complex eigenvalue. You can either look for completing the square or use quadratic formula to figure out what they are. Pick the eigenvalue. I always recommend the plus. Find your a minus lambda I, simplify, figure out the vector, break your vector up. And you're only going to do one of your eigenvalue eigenvector pairs because we're going to say, our pieces look like e to the lambda t eigenvector, and then by breaking up into the imaginary part and the real part, we get our solutions. And then, of course, we solve for initial conditions. And usually initial conditions aren't too bad because a good chunk of it will go away, especially this time. But usually a good chunk goes away in any case. And then we get our answers, our lovely, lovely answers. All right, good. Well, now we're ready. Should we ever see a complex root problem again, we know what to do. So our next problem. Solve for x of t and y of t satisfying the following system. X prime equals 5x plus 9y. Y prime is minus x minus y, where x of 0 equals 0 and y of 0 equals 2. All right, well, let's begin. Of course, the first thing we always do on these things is we say, well, what method should we use? And for systems, our default method is eigenvalue method. So we say, let's write this as a system in terms of a matrix. So we get x prime equals the coefficients, 5, 9, minus 1, x. Say, great. Our answer lies in understanding that matrix. And the first thing we want to understand about that matrix are the eigenvalues. So we take a minus lambda I, which of course that just means we subtract lambda on the diagonal. And we just work our way through. So 5 minus lambda, minus 1 minus lambda, subtract, minus 1 times 9. So let's see, what would that be? Minus 5 lambda, plus lambda squared, and plus 9, which looks like lambda squared. Lambda minus 5 lambda is minus 4 lambda. And minus 5 plus 9 is plus 4. Ooh, that factors. It actually factors pretty nice. Wow, who would have thought? Well, we kind of suspected, right? Given what we wanted to talk about, we're like, well, it's probably going to be either complex or repeated roots. And this is a repeated root. And so, our eigenvalues are 2 and 2. Good. Now remember, we can always check, like, I'm kind of skeptical. If you add your eigenvalues, that should be the sum of your diagonal entries. 2 plus 2 is 4, 5 plus negative 1 is also 4. If you multiply your eigenvalues, 4, that's the determinant. That's minus 5 plus 9. Yeah, so good. Definitely our eigenvalues are 2. Now, next step, eigenvectors? Well, there's a process here as well. But I can tell you right now that after you do these for a while, you're going to say, oh, every time we have a 2 by 2 and we have a repeated eigenvalue, we're going to come up short. Yes, 100% true. Now, I will say that's not 100% true in general. There is a time when you don't come up short. It's called the boring situation, where you have no interaction between x and y. We don't consider that. So if you see repeated roots, you should be like, oh, I'm going to come up short on my eigenvectors. Whoa! Well, let's find out if we actually do. We still have to do the process, right? So we take our a minus lambda I. Okay, so it's like we come up here and put in 2. So we're going to get 3, 9, minus 1, minus 3, times something, and we want it to be 0, 0. Now, we could, of course, do many things. I'm just looking for a row. Like the bottom row seems a little bit simpler, so I can just use this row. So as I go from left to right, I'm just going to fill in from top to bottom. So minus 1, minus 3, and then I'll have to flip the sign. So I'll put it as 3 minus 1. All right, so the claim is 3 minus 1 is our eigenvector. This can be checked in a lot of ways. For example, if you take 3 negative 1 times the original matrix, you'd have 15 minus 9 is 6. Well, that's 2 times 3. And then you'd have minus 3 plus 1, which is minus 2. Well, that's 2 times minus 1. Now you can also check it here. Now, you might say, but how do we know that's our only one? Well, because the more long way to do this is to say, oh, multiply by AB equals 0, 0. And this leads to two equations, 3a plus 9b equals 0, and minus a minus 3b equals 0. But they're not really two equations. It's really one equation, because they're scalar multiples of each other. So we're like, oh, well, gosh, let's just cross one equation off. And then that says, well, solve for a equals minus 3b. So that our eigenvector, AB, has to look like minus 3b, b, or b minus 3, 1. Which here, this is the case when I chose b equals negative 1. But it's some multiple of that. So that says, hey, there's only one eigenvector up to scale. All right. Well, what to do? Okay, so remember, there are two methods at this point, and let's talk about our two methods. Well, let's just do them one at a time. So method 1, and this is, if you like, we'll call this the book method, and this is the bottom up. Okay, so what the bottom up method says, okay, you find the eigenvector first, and then you find the correction term. Now, what do we mean by the correction term? Well, the thing is, with only one eigenvector, we only have one of our solutions. So that would be x equals some multiple e to the 2t times minus 3, 1. We're missing our second solution. So the question is, what is the second solution? Okay, so the way we do it is we say, okay, we start with our eigenvector already. So I'll call it u. Here's our eigenvector, and we want to find a v, so that if we take our a minus lambda I times v, we get out u. All right, well, what's the v that does this? Well, we take our a minus lambda I, which conveniently enough is right over here. So we need 3, 9, minus 1, minus 3, times some vector, and we need to get out minus 3, 1. any vector that does that will work. Anyone that does that. Now, you can probably guess one, but all right, let's suppose we weren't good at guessing. I mean, we should get good at guessing. We put in AB for the time being. We say, oh, well, that's like saying 3A plus 9B equals minus 3, and minus A minus 3B equals 1. And then you're like, well, oh, wait, they're the same equation. Yeah. It is the same equation. Knock one out. And you're like, all right, well, I can make lots of choices for A and B. Here's an easy choice. Just choose A equal minus 1. So our desired vector V is going to be our minus 1, 0. So here we choose A equal minus 1, B equals 0. Now, why do we call this the bottom-up approach? Well, because our second solution will have the following form. So we'll put some space here. So our second solution namely has the form as follows. X equals our e to the lambda t times u, tu, I should say, plus v. So in other words, our eigenvector got bumped by a multiple of t, and then there's a little bit of a correction there. Remember that this correction isn't unique because there's many choices you could have made. Choose simple. Don't try to be complicated. Try to keep things simple. All right, so we already know our e to the lambda t is e to the 2t, and then we have t times our vector, negative 3, 1, plus our correction. And there we go. So that's the second solution. And now we have our general form. But we have initial conditions. So we've got to satisfy those initial conditions. All right. So let's plug things in. We know x of 0 equals 0 and y of 0 equals 2. So if we plug in t equals 0, what do we see? Well, we see that we'll have 0, 2. So I'm just thinking of stacking our initial conditions is equal to a minus 3, 1. And then here, the 0 knocks that out, plus b minus 1, 0. Or we could say, hey, 0 equals minus 3a minus b, and 2 equals a plus 0b. By the way, having a 0 here is nice. Now, why did we have a 0 here? Because we chose simple. That's why we like to choose simple. Choosing simple gets us zeros. Having zeros make things easier to compute. So we say, we now know a equals 2. On the other side, here, this will tell us that b equals 3a. And so, 3 times b equals, negative 3a. Don't forget the sign. So we say, negative 6 equals b. And now we have a and b, and therefore we can write our answer. So x equals 2e to the 2t times negative 3. That's minus 6, right? 2 times negative 3, e to the 2t. And then we have b equals negative 6, right? So negative 6, and then you have a minus 3 times negative 6, so that makes plus 18. E to the 2t times t, don't forget there's a t there. And then you have negative 6 and a negative 1. So that makes plus 6 e to the 2t. So negative 6, negative 1, e to the 2t. If you clean that up, you'll see the negative 6e to the 2t and the 6e to the 2t cancel, so you actually get x equals 18 e to the 2t. On the other hand, y, well, that's the lower terms. So a equals 2. So you get 2e to the 2t. Oh, whoops. Haha, I forgot to put a t there. There's a t. All right, anyways, back to this. So 2e to the 2t. And then here we have minus 6 times 1 times all the rest. So minus 6. And this time I'll put the t in the front. T e to the 2t. And 0. Okay. So there's the answer. X equals 18 t e to the 2t. Okay, I wrote it in the wrong order. I should say I wrote it in the unconventional order. And y equals 2e to the 2t minus 6t e to the 2t. All right, so that's the bottom-up method. And if you read the book, which of course we all read the book, right? That's the way the book would do it. But now we're probably saying, hey, what's method 2? All right. We'll need another piece of paper here. So we're going to cover up all our beautiful work we did with method 1. And we hope that we get the same answers. We will. We'll get the same answers. Because it doesn't matter how you solve a problem, because it won't change the answer. So method 2, this is top down. Okay, so how does top down work? Well, instead of saying, oh, here's an eigenvector, find something that works up here, it says, oh, find something that works here, and then push down. So we still have that our second solution, so recall, we said our first solution was a e to the 2t, and I'll go ahead and call it, well, I'll just say what it is right here, 3, negative 1, plus, there's a b, e to the 2t, times, there's going to be a t u plus v. So the difference in approach is, in the first case, method 1, we had u, then we found v. The second case, we're first going to get v, and then we're going to get u. So in other words, which one of these do you find first? They might say, well, wait, we already have u, right? So shouldn't we find v first? And the answer is, well, hold on. Wait, hear us out. Okay, so what we do is we look at the following. We look at our a minus lambda I squared. Well, that's our 3, 9, minus 1, minus 3 times 3, 9, minus 1, minus 3. And, okay, so we have 9 subtract 9, which is 0. 27 subtract 27, which is 0. Minus 3 plus 3, which is 0. Minus 9 plus 9, which is 0. Okay, so the way we find v is we say, all right, what is some vector where a minus lambda I squared times v equals 0? We need a vector that does that. And we think about, what could it be? What could it be? And the answer is like, anything will work. Anything will work. And say, oh, well, that makes it really nice. And, well, for 2 by 2, anything will work. We're going to get into another discussion later on for what happens in 3 by 3 and higher. But it's a great discussion. I look forward to it. Keep watching. All right. So we say, well, let's pick our v to be 1, 0. Now, how do we get u? Well, then u would be equal to a minus lambda I times our v. So, in our case, that would be our 3, 9, minus 1, minus 3 times 1, 0, which would be, it turns out, 3 minus 1. Worked out pretty nicely, actually, in this case. And therefore, now we have our v and our u. So we have our second solution. So we say, hey, great news. We know the following. Namely, that x looks like a e to the 2t, 3 minus 1, plus b e to the 2t. Oops, I'm running out of space. I'm going to move this over a little bit here. b e to the 2t times rt u, 3 minus 1, plus rv, 1, 0. And now we say, wait, that's what we had before. Up to what? Well, up to a sign change. That was the only difference. So up to sign change, that's fine. No worries. No worries at all. Because this just pulled out a minus. And then the process from this point on for finding your A and B, it's still the same. Okay, so that's the idea. So those are the two ways. So whichever way you like to do it, that's fine. Whether you say, I have U, I'll find V, or whether it's like, I'll pick a simple V, and then I'll find, that'll give me a U, that's all right. Just make sure you know one way that you can do it, and then that you'll be able to get the answer. All right, well, good. Hopefully, we'll be pretty comfortable. And actually, in some sense, repeated roots are some of the most fun because some really cool stuff happens. And it's not a topic for today, but coming up really soon in the class, we're going to be like, ooh, we love repeated roots because it makes something really slick. So keep watching. It's going to be good, I promise. We're heading towards doing some 3x3 examples. And so we want to make sure we have the right context here. We've talked about 2x2, which essentially you could say that's like one bump. But 3x3, there's a potential for 2 bumps. How does it work? Well, there's a basic idea. So namely, it says, look, if an eigenvalue has repeated roots, right? So lambda shows up k times in the characteristic polynomial as a root. Then we say, well, how many eigenvectors? Well, if there's enough eigenvectors, life is good, no bumping required. So remember, it's not the repeated eigenvalues that are the problem, it's the missing eigenvectors. So when there's missing eigenvectors, we call it defective. Now we say, okay, well, suppose we have something that's like really defective, which is to say we have our nice eigenvalues, k times, but just one eigenvector. Then what can we do? Well, the answer is we can construct our solutions from the bottom up. Okay, great. Well, how do we do it? Well, the first thing is you find an eigenvector. Well, because there's one of them, right? So we find the one. And we make sure there aren't any others. Say, okay, well, that's V1. And to be an eigenvector means that A minus lambda I V1 equals 0. And this is really just a way of saying, oh, hey, A times V1 equals lambda V1. And now we say, all right, the next level up is we want something such that when I multiply A minus lambda I times V2, it produces V1. Okay, now that's what we were doing before. And then we're saying, okay, you multiply V1 by T and add V2. Now, notice that this is another way of saying this. It says, oh, AB2 has this really cool property. It's lambda V2 plus V1. And of course, we keep going up. If we have the next level, we bump again. But now, it's not multiplying by T. It's going to be 1 over 2 factorial T squared. Now you might think, why are we doing that? Well, the short answer is because that's what works. The long answer is because that's what we need to make it work. And so you might say, but why didn't we divide by 2 factorial when we were bumping before? In essence, we weren't doing it before because it was getting absorbed into the constant. Because constants are great at absorbing things. They're like sponges that way. Now, the reason we need it here, in fact, we'll go through it and work through an example in detail, is so that when we take the derivative of t squared, we can somehow compensate for the 2 that comes down. So that's actually what's happening. So that when I take the derivative of t squared, I can cancel out the 2. Now you might say, well, wait, the next level, when we take the next term, the 3 comes down, but 3 factorial doesn't cancel. Well, no, but it's 1 over 2 factorial, which matches what we have before. So that's what's going on. So anyways, this same process keeps going up. So you can think of that, like a v3 is lambda v3 plus v2. This is another way to say it. A v4 is lambda v4 plus v3. And dot, dot, dot. And you keep going. So notice the first v1, that's your eigenvector. And that's like something that gives your eigenvector. And there's something that gives the thing that gives your eigenvector, right? You just keep working. And this process will always succeed. In other words, the way you form this will always give a solution. So, or really I should say your linearly independent solutions. Again, this is from the bottom going up. We'll talk about the top going down when we do a problem. Now, you might say, okay, does that handle all situations? And the answer is no. Because this assumes, hey, we have an eigenvalue and just one eigenvector. But it's possible that you could have an eigenvalue that's repeated, let's say 3 times, and there's 2 eigenvectors. Now the question becomes, how do you start climbing? It gets a lot more complicated. And in that case, we'll see why things get complicated. Well, spoiler alert, something's coming. And we'll see that in that case, it really does pay to switch directions in which way we're going. Now, the more you do this, you might think, gosh, is there some better tool out there for helping us understand matrices? And it turns out that a lot of things that we're doing are sort of skirting around avoiding a particular topic in linear algebra called canonical forms. And canonical forms are saying, what is a unique way to write this matrix? And, well, there's a lovely question about what that means, but the topic, it's a little bit outside the scope of what we're able to do. If you want to know more, take more math, and of course, then you'll know more. But, all right, let's actually go through and say, why does it work? Why does all this work? So, I worked it out ahead of time, just for this occasion. Okay, so let's talk about x3. So I copied here x3, e to the lambda t, 1 over 2 factorial t squared v1 plus tv2 plus v3. And then I grabbed the notes that were written before. And now, what happens? Well, take the derivative. Now, we're going to have to do a product rule. Derivative of the first, lambda e to the lambda t. Everything else stays the same. And then, e to the lambda t times this derivative. Well, see, that's why things bump down. tv1 plus v2. All right, so here's x3 prime. And now I say, well, let's compute a times x3. So that's a e to the lambda t times our function. So that's just copying x3 again. The a comes in. And so you have AV1, AV2, AV3. And now we say, oh, well, wait. A times V1, lambda V1. A times V2, lambda V2 plus V1. And AV3, lambda V3 plus V2. and you rearrange, you see, okay, this term with the lambdas go in, and without the lambdas, they go in like that. All right. And it's our wonderful game of matching. And you just say, oh, look, matching, matching, matching. This matches that. And so that's the verification. And in some sense, you can say, oh, you know, what's essentially happening is it's kind of trying to mimic, in some sense, like a product rule, right? Derivative of the first times the second plus the first, right? The lambda is trying to say, oh, you're trying to take the derivative of e to the lambda t, and here this constant is like, oh, when you take the derivative of the other part. And so that's why it works out so nicely. So there you go. All right, well, there's the theory. Where's the practice? So let's look at this example. Find the general form for solutions of x prime equals 5 minus 1, 1, 1, 3, 0, minus 3, 2, 1, x. And it says, hint, for the matrix, we have a minus lambda I is minus lambda minus 3 cubed. All right, good. They saved us a few steps. And in particular, we say, oh, that tells us that we have eigenvalues are all 3. 3, 3, 3. Okay, so next up, let's deal with eigenvectors. So we're going to look at our a minus lambda I. And when we do that, we're going to have, well, it's always 3, so it's subtracting 3 off the diagonal. So it's 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2. Okay, now, here we go. The fun is about to begin. I know you're thinking, Steve, we've been having fun this whole time. I feel the same way. All right, so remember, to be an eigenvector, we're going to take this and we're going to multiply by our ABC, and we want to get out 0, 0, 0. And we say, all right, well, let's see what this says. This leads to a system of equations. 2a minus b plus c equals 0. And then a equals 0. And minus 3a plus 2b minus 2c equals 0. Now there's a couple of things that we can figure out really quickly. First off, we can figure out what a needs to be. 0. Okay, that was easy. And so we say, oh, well, we know a equals 0. And then, if you look here, that says, oh, minus b plus c equals 0, or b has to equal c. And here, a equals 0, we get 2b minus 2c equals 0, or b equals c. In other words, these other two equations become the same. So what does that say about our eigenvector? Well, first off, it says the following. It says, hey, if I have an a, b, c, a has to be 0, and then b and c have to be equal, which says my eigenvector is some multiple of 0, 1, 1. So you say, there's only one eigenvector. All right. Well, Well, that means we're very deficient. Okay, good. So we know there's one. We've got our eigenvalues, we found our eigenvectors, and now we're ready to start working the problem. So we can start bottom up or top down. Which one should we do? Well, let's maybe start bottom up, the one we just talked about. Okay, so bottom up. Here we go. We know our eigenvectors. So that says, hey, we know our first level. U equals 0, 1, 1. We need to find a V, and we need to find a W. Now, how do we find V and W? Well, what we need is we need to have the following. So first off, where did U come from? That's A minus lambda I U equals 0. V will be A minus lambda I V equals U. And W will have A minus lambda I times W equals V. So let's try and find these vectors. So, well, okay, we start there. A minus lambda I V equals U. You kind of have to start there. You can't start over there because we have no idea what V is, so we can't find W. So we have our A minus lambda I. We're going to keep running that a lot. All right. And then we have times some vector equals 0, 1, 1. All right. So that's, we're looking for that. What makes that true? So we have an A, a B, and a C. And we start looking at this. Well, that says what? 2A minus B minus C equals 0. Here, you get A plus 0 equals 1. And then you get minus 3A plus 2B minus 2C has to equal 1. Now, the equation here, that tells us A equals 1. Great, we know A. So this tells us, oh, we need B plus C equals 2. Now again, A equals 1. So if you say, oh, that's minus 3, so 2B minus, oops, did I copy something down right? Ah, I did. This should be a plus there. I'm so sorry. So that should be not B plus C, that should be B minus C. Ha 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 ha. B minus C equals 2. Yep, double check. If we put in A equals 1, it says 2B minus 2C equals 4, or it says B minus C equals 2. All right, so we just need a choice for B and C where this is true. I like to choose things which are 0 as often as I can, so let's just say, let's choose C equals 0. It's a choice. We made a choice. So we say, all right, we'll choose B equals 2 and C equals 0. And that says, aha, our A, B, C is R1, 2, 0. So that goes there. All right, we still need to find W. So we'll run out of space. That's okay. That's why we have more paper. If I can get the page, there we go. All right, so let's cover up what we just did. We know what V is, and we know what we're looking for. A minus lambda I W equals V. So we again copy A minus lambda I. So that's going to be 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2, times some vector A, B, C, and we need to get out 1, 2, 0. Okay, good. Now, work the system of equations. So I'm going to move this up for a few minutes just so I have more space. All right, we get 2A minus B plus C equals 1. A plus 0B plus 0C equals 2. And then minus 3A plus 2B minus 2C equals 0. All right, well, we know what A is. A is 2. So we can put in A equals 2, and that says, oh, minus B plus C, well, that's 4. We subtract, that's negative 3. Now here, we have minus 6. We move it across. We get 2B minus 2C equals minus 6. So in other words, these will become the same. All right, well, now more choices, right? And you say, hey, again, choose simple. Say, look, choose b equals 3, c equals 0. That's very simple, and it works. And therefore, we say, aha, our desired ABC is A is 2, B is 3, C is 0. 2, 3, 0. So there's our W. All right. Now, are we done? Well, almost. We now have to put them all together. So we just have to remember what our general form looks like. So our general form, we have our e to the lambda t, whoops, there's an a, times u. So it's our, it's our traditional, e to the eigenvalue, t, and then our eigenvector. Plus, our next level will be b, e to the lambda t, and then comes our first bump, tu, so this gets bumped up, plus v. And then our last piece will be c, and then we'll have e to the lambda t again, one more bump. But remember, there's this curious thing that happens here. So it's not just multiplying by t, it's 1 over 2 factorial, which is 1/2 t squared u plus tv plus w. And there's our answer. We just fill in our pieces, and life is good. So we have a, e, lambda equals 3, 3t times 0, 1, 1. Plus, then we'll have b, e to the 3t. Then we have t, 0, 1, 1, plus 1, 2, 0. Plus c, e to the 3t. 1 over 2t squared, 0, 1, 1, plus t, 1, 2, 0, plus 2, 3, 0. And there we go. There we go. There's our answer. Now here's a couple of things to think about. What would have happened if we tried to climb up again, right? Because we're sort of starting at the bottom and working our way up, 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 up. Would it have worked? Could you have taken one more step? What do you think? Should we try it? Yeah, let's try it. All right, let's try to take one more step. One more step. Okay, so here we are trying to take one more step. Now, in principle, we know this should fail. But let's actually see it fail. And you may say, wait, how do we know it's going to fail? Well, because if it didn't fail, we'd have found another solution. That's why we know it's going to fail. Okay, so we have our matrix. And then we're saying, all right, is there an A, B, C, where this is equal to 2, 3, 0. Now, what happens? We get a series of equations. That's not too surprising. 2a minus b plus c equals 2. And then we get a equals 3. And then we get minus 3a plus 2b minus 2c equals 0. Now, a equals 3. Nothing wrong there, but we plug that in. That says 2a will be 6. Move it across. Minus b plus c is negative 4. Here, we get minus 3 times 3. Well, that's 9. Move it across. We get b minus c. And if you move it across and divide, is 9/2. Well, is it possible for minus b plus c to be negative 4 and for b minus c to be 9/2? The answer is no. Wah, wah, wah. It fails. But that's okay. It failing is a good thing because we knew it should fail. So, all right. So there we go. Now, bottom up. What about top down? Let's do it. Okay, so here we already know that we're deficient in 1. We're still going to find our same idea here, right? Our same idea. We're still going to find u, v, w, but now instead of starting with u, we're going to start with w and go back. Okay, so, whoops, aha, there's too many pages here. So here we go. We're going to call this our, not surprising, our top down. All right, we start by doing what? Well, we're going to start by finding our w, which because we have deficiency, only one eigenvector, but there's 3 eigenvalues, I'm going to look at a minus lambda I would be the base level. A minus lambda I squared is 1 up. So I'm going to look at a minus lambda I cubed. So we need to look at a minus lambda I cubed. So we're going to take our matrix, 2, minus 1, 1, 1, 0, 0, and minus 3, 2, minus 2 cubed. All right. Now, I'm going to tell you right now, it's going to be the all zero matrix, but in the interest of fairness, we're still going to run the computation. Okay, so just feel free, if you like, to be like, all right, I know where this is going, Steve. I'm going to fast forward a few minutes. I know how you feel. So we start writing these out. Okay, so I'll just copy the first matrix over. And we have 4 minus 1 minus 3. That's 0. Minus 2 plus 0 plus 2. 0. 2 plus 0 minus 2 is 0. All right. Oops, I was putting the wrong one. That's all right. 2 plus 0 plus 0. 2 minus 1 plus 0 plus 0. Minus 1. 1 plus 0 plus 0, which is 1. Minus 6 plus 2 plus 8. Ooh, that one. Oh, not plus 8, plus 6 again. All right, let's do that one more time, Steve. I'm from a studio audience, right? I can't make this mistake. Minus 6 plus 2 plus 6 means a plus 2. 3, 0, minus 4, minus 1. Minus 3, 0, plus 4, plus 1. All right. Then we have 0, minus 2, plus 2, 0. And then we have a 0, plus 1, minus 1, 0. 0, minus 1, plus 1, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0. We like zeros. 0 plus 4 minus 4, 0. 0 minus 2 plus 2, 0. 0 plus 2 minus 2, 0. Whoa! Who knew? Who knew? Okay. All right. Good. Whew. Nice. Nice. All right. Now, here we go. What do we need? Well, we need to pick first our W. Now, how do we do it? Well, we look at a minus lambda I cubed, W equals 0, and we're saying we want some vector where this is true. Now in our case, that says, okay, we're looking for some vector where when we multiply, we get 0, 0, 0. All right, can we think of any vector that works? Any vector at all that works? And I think we can probably think of a whole bunch of vectors. So like, there's so many vectors. Okay, all right, let's pick something super clean. Let's pick 1, 0, 0. Okay, I think that's pretty clean. All right, so we're going to pick 1, 0, 0. All right, so great. That's wonderful news for us. So this is our vector W. Now, once you have W, V and U are automatic. Because what? Well, because how everything's related. So in particular, we say, okay, from W, we can get V by A minus lambda I times W. So we say, all right, well, that's our 2 minus 1 minus 1, 1, 0, 0, minus 3, 2 minus 2, times 1, 0, 0, and we carry it out, because 1, 0, 0 is actually pretty straightforward. That's 2, 1 minus 3. Now, that's our V. What's our U? Well, our U is A minus lambda I times our V. So 2 minus 1 minus 1, 1, 0, 0, minus 3, 2 minus 2, times our 2, 1 minus 3 gets us what? Well, 4 minus 1 plus 3, right? Have I copied something down right? I have not copied this down right. That should be a plus 1. Whew, something weird was about to happen. 4 minus 1 minus 3 is 0. 2 plus 0 plus 0 is 2. And then minus 6 plus 2 and a plus 6. 0, 2, 2. And now we have our UVW. And once we have our UVW, that's what we need, because it's the same process as before in terms of U, V, and W. And so we can just now grab that part, U, V, W, and we can write down our answer. It'll look slightly different, but it's okay to look different as long as we're equivalent. So our answer here, well, X would equal, and well, our constant A, e to the 3t times u, 0, 2, 2, plus our B, e to the 3t times our t times u plus our v. So t, 0, 2, 2, plus our v, which is 2, 1, minus 3, plus some constant c, e to the 3t, and now we have our 1 over 2 t squared, 0, 2, 2, plus our t, 2, 1, minus 3, plus our w, 1, 0, 0. Now, you might say, hey, if I compare my two answers from the two different approaches, that is to say, the top down versus the bottom up, they don't necessarily look the same. They don't have to look the same, but they're equivalent, which is to say, any solution that you can get from one, you'll get from the other as well. All right. So at this point, you might be saying, cool, cool, cool. Are there any worries about the top-down method? Because this seems to be pretty slick. And the answer is yes, you can run into problems. And so let's talk about the kind of problem you might run into and why it's not so terrible and how to live with it. Okay, so I am going to, we'll move this up. All right, we have a lot of paper here. Okay, here's the thing. We made a choice here. In this case, we were like, oh, we just need to pick something where we got, ABC multiplied, got 0, 0, 0. There's actually a subtlety. We have to pick a W so that these three vectors, W, V, and U, are all non-zero. So if you make a bad choice for W so that you get a 0 by the time you hit U, it means that choice is wrong. It won't work. Now, you might say, well, could that happen? Check this out. Sorry, I read my notes wrong. So, let's try this one more time. All right, what could we have done? Well, we could have picked W equals 0, 1, 1. And now, if we pick our V, that's A minus lambda I times W. Well, okay, that's our 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2, times 0, 1, 1. And if we carry out the multiplication, we'll get 0, minus 1, plus 1, 0, 0, 0, minus 3, plus 2, minus 2, which is 0, 0, 0. And then U, of course, which is A minus lambda I times V, well, will also be the 0 vector. Now, why is that bad? Well, because when we come up to our solution, we're going to get zeros here, which is like worthless. So here's the thing. We just have to be careful. Make sure we pick our W so that both V and U are non-zero. That's what you have to worry about. They might say, well, what happens if I pick a bad W? Because it is possible to pick a bad W. And the answer is, well, first off, pick it simple. So like 1 and the rest be 0. And if that fails, go 0, 1 and the rest 0, or 0, 0, 1 and the rest 0. The moral is somewhere where you just have a single 1 and the rest of the entries are 0 will work, and it's guaranteed. So it really simplifies your search space. There's not a lot of guessing that has to go in. So that's why, start with the obvious guess. And if that one didn't work, go with the next obvious guess, and so forth and so on. All right, good. So, success. We know how to answer this type of problem. Woohoo! All right, well, maybe one more? Maybe. Now, before you start this problem, I recommend you go get something to eat. Maybe pop some popcorn, get a drink. We're going to be here a while. We're going to go all the way through this problem. And there's going to be a lot of discussion, a couple of nice ideas, and it's going to be interesting. So, all right, I hope you're ready. Let's begin. All right, so find the Saltulian. Wait, that probably shouldn't be Saltulian. Let's say it probably meant to say solution. All right, find the solution. There we go, much more reasonable. For x prime equals 2, 1, 2, 3, 0, 2, minus 6, minus 2, 5, x. And there's an initial condition. X of 0 equals 2, 4, minus 1. Okay, so let's begin. There's no hints. We're not being told what the eigenvalues are. No hints about eigenvectors. So this is why we got to take our time and, enjoy the process. Savor the method. So we begin. We're going to do this whole problem. And, well, it's good to do once, right? All the way through. Just so you can say, yeah, we've done it. We know how this works. All our pieces. So we're taking our 3 by 3 determinant. So we have our diagonal. So this is going to be the action one, 2 minus lambda, minus 5 minus lambda. And then 1 times 2 times minus 6 is minus 12. 2 times 3 times minus 2 is also minus 12. So, okay, very minus 12 heavy. Those are our diagonals in one direction. Of course, we got to do our diagonals in the other direction. All right, minus 6 minus lambda 2. That would be a 12 lambda, but because we're going in our other direction, we're going to subtract 12 lambda. Minus 2 times 2 times 2 minus lambda, so that's 4 times 2 minus lambda, but, well, negative 4, but of course we subtract, so it becomes a plus 4 times 2 minus lambda, and then we have a minus 5 minus lambda, a 3, and a 1, so we're going to subtract 3 times minus 5 minus lambda. Okay, cool. Now, for our first one, let's pull out the minus lambda for a second. I'm going to multiply the 2 minus lambda by the minus 5 minus lambda. So that would be minus 10 and minus 2 lambda plus 5 lambda plus lambda squared. Then we have minus 24. And we have minus 12 lambda. We have plus 8 and minus 4 lambda plus 15, okay, and plus 3 lambda. All right, which we can now distribute this through. Minus lambda times lambda squared is minus lambda cubed. Minus 2 lambda plus 5 lambda becomes 3 lambda times minus lambda becomes minus 3 lambda squared. Then we have a 10 lambda. We subtract 12 lambda, so that gets us to minus 2 lambda. Subtract 4 lambda gets us minus 6 lambda. Add 3 lambda gets us to minus 3 lambda. And then we have minus 24 plus 8 plus 15. Now 8 plus 15 would be 23. Minus 24 plus 23 makes minus 1. So this is minus lambda cubed plus 3 lambda squared plus 3 lambda plus 1. Now, if you were really good at algebra and your instructor was like, I'm going to make sure you remember these numbers so that someday you're going to be like, I remember this. Do you remember where these numbers show up? This comes from a binomial theorem, and it turns out that this is minus lambda plus 1 cubed. All right, so our eigenvalues are minus 1, minus 1, minus 1. Okay, good. Whew, nice. Now, the question, eigenvectors. So, we turn to that. So we're going to take our minus 1, a minus lambda I. So minus 1 makes plus 1. So that gives us 3, 1, 2, 3, 1, 2, minus 6, minus 2, and let's see, minus 5 plus 1 makes minus 4. All right. So, and now we're going to multiply this by A, B, C, and we're going to get 0, 0, 0. So we write out our equations. we have 3a plus b plus 2c equals 0. 3a plus b plus 2c equals 0. Minus 6a minus 2b minus 4c equals 0. And now you're like, oh, wait a second. What do you notice? That first and second equation are the same. And actually, if you multiply the first equation by -2, it's the third equation. So there's one equation here. What does that tell us? Well, that tells us any choice for A, B, C works as long as 3a plus b plus 2c equals 0. Now, in particular, notice here it says, oh, I can choose b to be equal to minus 3a minus 2c. So that tells us our eigenvectors a, b, c look like a minus 3a minus 2c, c. Well, you can pull it apart. And the way you pull it apart is you say, all right, which things have a, which things have c. It's the same idea we did way back at the very beginning of this set of problems. We talked about complex. So we say, oh, if in terms of the a, we get 1 minus 3, 0. And in terms of the b, the c, we'll get 0 minus 2, 1. So how many eigenvectors do we have? Well, these are both eigenvectors. So we have 2 eigenvectors, 3 eigenvalues, 1 short. All right. So here's where we're at. We now know, after all this work, that both of these are eigenvectors. Oh, so make a note. These are our eigenvectors. And they are clearly different. In a sense, I can't scale this one by some number to get that one, or vice versa. So our general solution for this, and I know we're after a particular solution, but if you're going to get a particular solution, you start with a general solution. Our general solution will look something like the following. Some a e to the minus t, this minus t because our eigenvalue is minus 1, times our 1 minus 3, 0, plus our b e to the minus t, times our 0 minus 2, 1, plus c times something. And this is where we're going to spend a fair amount of time asking the question, what's in the box? What's in the box? All right. Well, what's in the box? We have to figure that part out. So let's start with bottom up, right? Sure. Why not? Okay, so I'm going to put this aside. We'll pull it back when we need it. I have it right here for reference. And of course, I hope you have it for reference too, because you probably have it scanned in. So you're about to, you see what's coming. You're like, oh, Steve, I've got some bad news for you, my friend. I know. Okay, so let's talk about our bottom-up approach. So here's what we have. We have 2 eigenvectors. We need one more. And so our last solution really has the form tu plus v times e to the minus t, where u is an eigenvector and v is of the form a minus lambda I times v equals u. So that's what we're doing. So we're starting with our eigenvector. We're going to find v. Now, at this point, you're probably saying, oh, great, good news, Steve. you actually have some choices. Okay, so let's try things. So let's try u equals our 1 minus 3, 0. All right, and well, okay, so we're going to take our a minus lambda I, that's here in this corner, and we have 3, 1, 2, 3, 1, 2, minus 6, minus 2, minus 4, times our a, b, c, and we want to get out 1 minus 3 and 0. Which leads us to a system of equations, namely 3a plus b plus 2c equals 1. 3a plus b plus 2c equals minus 3. And minus 6a minus 2b minus 4c equals 0. And at this point, you're like, uh-oh, that's impossible. It fails. Oh, no, it doesn't work. So, it's not this eigenvector. And now you're like, sweet. No worries, Steve. We have a second one. All right, cool. Let's do that. Okay, so we grab our second eigenvector. So it's 0, minus 2, 1. And we start the process. And we have our a, b, c equals 0, minus 2, 1. We get 3a plus b plus 2c equals 0. 3a plus b plus 2c equals minus 2. And minus 6a minus 2b minus 4c equals 0. And now you look at this and say, fiddlesticks. You probably didn't use fiddlesticks. You probably had some more interesting language. But look what's happening. It's happening again. It's impossible. Now at this point, you're probably starting to say, wait, did we miss an eigenvector? I thought we just had 2 of them. Because we said it right here, right? There's eigenvectors we can count, 1, 2. Like, okay, there's 2 eigenvectors. We've tried them all. Or have we? So this gets into an interesting question. How many eigenvectors are there? Now you're probably thinking like, well, there's 2, Steve. You found them. You listed them. But actually it turns out that you have to be careful, because when we have just one eigenvector, remember, one eigenvector is not unique because we can always scale it. So we can take any multiple of it. When we have 2 eigenvectors, things get more interesting, because what happens, here we can think of it, there are 3-dimensional vectors. So we have one vector that points in one direction, and a second vector which points in some other direction. But we can take any combination of those 2 vectors. So in fact, there's not just 2 possibilities, there's infinitely many possibilities, because we can combine them together in infinitely many different ways. And so we have a whole menagerie of potential eigenvectors. In other words, there's infinitely many choices out there. We've only tested 2 of them, infinitely many left to check. And so at this point, you probably are like, that sounds dangerous, Steve. And the answer is yes, that is incredibly dangerous. And so what happens? Well, we need to think of a better way. Now, there's a couple of things that we could do. We could say, well, we just need to make sure that we choose the right combination of these 2 vectors here so that we get to a system of equations. But that sounds like work. And I'm like, isn't there a better way? And there is. So let's finish our note here. With 2 eigenvectors, we can combine in infinitely many different ways. And so there are many possible choices for you. And most of them won't work. In fact, essentially, there's infinitely many directions we could go. One direction works. And so it's like finding a needle in a haystack when we're working from the bottom up, because we have to find the right bottom. That sounds like it might be taken out of context if I say that out loud. Forget I said find the right bottom. We have to find the right place to start. There we go. That's much safer. No one will get me in trouble for saying that. And knowing where to start can be very hard. So that's why it's not always in our interest to start at the lowest level. So let's switch gears. Let's do a top-down approach. All right, so there we go. We're switching gears because bottom-up will inherently fail. All right, so grab more paper because, well, you can always use more paper. And here we go. So we are going to go from our top down. Now, what do we need? Well, we're going to have, because we just need one level, we're going to need to find some a minus lambda I squared times our vector, let's see, hold on, I want to make sure I get this right, v equals 0, and then our u will equal a minus lambda I times v, and then our solution, it will be e to the lambda t times our tu plus v. There we go. That's what we're after. All right, well, so where do we begin? We start with a minus lambda I squared. So a minus lambda I squared is going to be equal to, well, 3, 1, 2, 3, 1, 2, minus 6, minus 2, minus 4, 3, 1, 2, 3, 1, 2, minus 6, minus 2, minus 4. And we carry out this multiplication. We have 9 plus 3 minus 12, 0. 3 plus 1 minus 4, 0. 6 plus 2 minus 8, 0. All right. 9 plus 3 minus 12, 0. 3 plus 1 minus 4, 0. 6 plus 2 minus 8, 0. You're probably getting a little bit like, oh, it's lots of zeros. Yeah, it's going to be a lot of zeros. No worries. Minus 18 minus 6 plus 24, 0. Minus 6 minus 2 plus 8, 0. Minus 12 minus 4 plus 16, 0. You might be wondering, do we always get all zeros? Essentially in a lot of these simple cases, but again, things can get much more complicated. Now we ask ourselves the question, what v should we pick? So we have 0, 0, 0, 0, 0, 0, 0, 0, 0 times our a, b, c. We want to get 0, 0, 0. And we go with the philosophy, when we can, pick simple. And we could pick 1, 0, 0, 0, 1, 0, 0, 0, 1. Those are the simple choices. We can do this sort of arbitrarily, or we can kind of be smart. So what do I mean by smart? Okay, if we pick, so if we say v is 1, 0, 0, then u would be what? Well, if I multiply a matrix by 1, 0, 0, it's grabbing the first column. So it'd be 3, 3 minus 6. If we picked it 0, 1, 0, this grabs the second column. So that would say u is 1, 1 minus 2. If we picked v to be 0, 0, 1, that's picking the third column. That says u would be 2, 2 minus 4. Now, it doesn't matter. They're all going to be right. But I'm somebody who likes things simple. It's in my nature. So I'm going to grab that one, because that seems to have the simplest numbers involved. So we say, aha, life is good. We have our v, we have our u, and therefore our last solution is going to be the following. It is going to be e to the minus t, because all our eigenvalues were -1. And then we're going to have t times u, 1, 1 minus 2, plus v, 0, 1, 0. Now, before we go and plug that back in, I do want to make a comment here. Do you notice anything about the vector 1, 1, 2? 1, 1, negative 2 that we just wrote down. Well, if you look at this vector 1, 1, negative 2, and you compare it to 1 minus 3, 0, and 0 minus 2 plus 1, you will come, after some time, to the aha idea that says, oh, 1, 1 minus 2 is equal to 1 times this vector plus -2 times that vector. Which is to say, 1, 1 minus 2 is an eigenvector of our original system. It's just not the ones that we naturally chose. So here's the problem that we were talking about before. Remember when we were doing our bottom-up approach, we said, well, what's the right choice for our eigenvector? Because there's lots of choices, and it wasn't so clear. But now we're like, oh, the right choice would have been 1, 1, negative 2. So if we had made that choice, we'd be like, aha, life is good. Now in this case, it turned out it was a column. Well, maybe that's a good clue for 3 by 3. But of course, things can always get more interesting. Yeah, of course they can. Of course they can. All right, so back to our problem. Where are we at? Well, we just found our last solution. So we're going to go back to our first page here, and where we had this, and we're going to write down our last piece. So our last piece is e to the minus t times t, 1, 1 minus 2, plus 0, 1, 0. All right, good. And are we done? No. Oh, Steve. What's left? Initial conditions. Okay. So we are after the choice for A, B, C, where we get 2, 4, minus 1. All right, so let's do some copying here. We'll switch to another color. Why not? All right, so we'll say here's our general solution. X equals A, e to the minus t, 1 minus 3, 0, plus B, e to the minus t, 0 minus 2, 1, plus C, e to the minus t, times t, 1, 1, 2, 1, 1 minus 2, excuse me, plus 0, 1, 0. And we want x of 0 to be 2, 4, negative 1. Now, on a side note, I'll be honest with you. This is my first time doing this problem. So I have no idea if these numbers A, B, and C are going to be nice. I'm hoping they are, but I don't know. Well, time to find out. So when we plug in 0, what do we get? We get a times 1 minus 3, 0, plus b times 0 minus 2, 1, plus c times 0, 1, 0, which becomes what? Well, the top line tells us 2 equals a plus 0b plus 0c. So 2 equals a. Oh, that'll be easy to solve. The middle, 4 equals minus 3a minus 2b plus c. And the bottom line tells us that minus 1 is a times 0, which is 0, plus b, which is b, plus 0c. Oh, so we actually know a right away, we know b right away, and then c, well, that becomes 4 plus 3a, 6, and then plus 2b, so that's minus 2. And so, okay, 4 plus 6 minus 2 is 8. All right, cool. So we are in our home stretch. So x equals 2 e to the minus t, 1 minus 3, 0, and then minus e to the minus t, 0 minus 2, 1, plus 8 e to the minus t. And here, let's go ahead and put those together. So we're going to get t, t plus 1, and minus 2t. Well, we can mush this all in into one nice expression. Okay, so let's be careful here. We'll have 2 e to the minus t, 0 e to the minus t, and 8 times e to the minus t times t. So that we can write it as 8t e to the minus t plus 2e to the minus t. Here we'll get a minus 6 e to the minus t. Here we'll get a plus 2 e to the minus t. Here we're going to get a plus 8. Well, okay, put that all together. That'll become a 4 e to the minus t. And then we get an 8 times t e to the minus t. All right, and then in our last entry, well, we're going to get 0 there, a minus e to the minus t, and a minus 16t. So minus 16t e to the minus t. Oops, I forgot my plus in the previous line, and minus e to the minus t. Oh, wow. You can almost make a whole exam off this one problem. There's so much going on. We won't. Don't worry about it. But just know it is possible to do these things. You can do it. You have the tools. You need practice. And when you start, and the more you practice, the more sort of automatic things will become. Keep at it. You can do it. I believe in you. All right. Well, thanks for being so patient and for working all the way through this last problem with me. I hope you do great. I hope you're getting more comfortable. And please don't make these last two problems make you nervous. Just to show you some of the things that can happen. All right. See you later. Bye.